At this very moment, something extraordinary is happening to you. It is silent, it is invisible, it is completely beyond your senses. Yet it connects you to the most violent and fundamental processes in the cosmos. Trillions of tiny ethereal particles are passing through your body every single second of every single day. These particles, called neutrinos, have journeyed from the fiery heart of our sun, and now they are piercing through you as if you were not even there. Almost every single one of them will continue, unimpeded, straight through the entire Earth, exiting the other side without interacting with matter. This simple fact presents us with a profound cosmic puzzle. How can something so incredibly abundant, something that fills the entire universe in such vast numbers, be almost impossible to detect? It is a paradox that has fascinated and frustrated physicists for nearly a century. This isn't a question of technology alone. It is a question that probes the very nature of matter and the fundamental forces that govern our reality. The story of the neutrino is a detective story on a cosmic scale. We will follow the evidence, from a theoretical puzzle on a blackboard to the construction of some of the largest scientific instruments ever built. Our investigation will take us deep beneath the ground and ice. There, we will see how scientists manage to catch a fleeting glimpse of these phantom particles. This is the story of the neutrino, among the most abundant, yet most elusive particles we have ever known. So, what exactly is a neutrino? To truly understand this elusive entity, we must journey to the very heart of matter, to the blueprint of reality known as the Standard Model of Particle Physics, which describes the known elementary particles and 3 of the 4 fundamental forces, excluding gravity. This elegant yet incomplete theory describes all the known fundamental particles and the forces that govern their interactions. Within this framework, we find 2 main families of matter particles: the quarks, which bind together to form protons and neutrons, and the leptons. The neutrino belongs to this second family, the leptons. The most famous lepton is the electron, the particle responsible for electricity and chemistry. But the electron is not alone. It has 2 heavier, unstable cousins, the muon and the tau. And each of these 3 charged leptons has a corresponding neutral partner: the electron neutrino, the muon neutrino, and the tau neutrino. These 3 flavors of neutrino are the fundamental particles we seek, the basic building blocks of our universe. But unlike its familiar cousin, the electron, the neutrino has no electric charge, so electromagnetic fields do not act on it. This neutrality is the first and most crucial key to its ghostly character. The universe is awash in electromagnetic fields. They are the cosmic puppet strings that pull and push on any particle with a charge, dictating its motion, binding atoms into molecules, and carrying light across the cosmos. The electron, with its negative charge, is constantly dancing to this electromagnetic tune. But the neutrino is blind to it because it carries no electric charge. It feels no electric pull, no magnetic push. It sails through the most intense magnetic fields and densest plasmas as if they were empty space. This profound indifference to the universe's most dominant long-range force is what begins to weave its cloak of invisibility. For decades, physicists believed neutrinos were not only neutral, but also massless, like photons, the particles of light. This was a core assumption of the original Standard Model. However, groundbreaking experiments, which we will explore later, revealed a shocking truth. Neutrinos do have mass, but it is an almost impossibly tiny mass, millions of times smaller than that of a single electron, the next lightest particle. This combination, absolute electrical neutrality and a minuscule mass, is a recipe for elusiveness. It allows them to travel across vast cosmic distances, carrying information from the heart of stars and the dawn of time, almost completely unimpeded. So if neutrinos ignore electromagnetism, and their tiny mass means gravity is negligible for individual neutrinos, how do they interact at all? They interact primarily via the weak nuclear force. As its name implies, this force is feeble compared to the strong force that binds atomic nuclei, or the electromagnetism that governs our everyday world. Crucially, it also operates only over incredibly short, subatomic distances. For the weak force to have any effect, a neutrino must score a direct bullseye hit on the nucleus of an atom, a target infinitesimally small. Think of the neutrino as the universe's most antisocial particle. While other particles are constantly interacting, colliding, deflecting, emitting and absorbing energy, neutrinos prefer to keep to themselves, their existence defined by what they do. This profound reluctance to engage with other matter is not just a quirk, it is their defining characteristic. The probability of a neutrino interacting, its interaction cross-section, is so small it defies everyday intuition. To put it in perspective, imagine a block of solid lead stretching for 1 light-year, that's nearly 10 trillion kilometers. If you were to fire a single neutrino at this impossibly dense barrier, it would have only a 50-50 chance of hitting a single atom along its entire journey. The rest of the time, it would pass straight through without a trace. This is the scale of their ghostly nature. And yet, despite their profound isolation, the universe is saturated with them. They are the second most abundant particle after photons. The most immediate and powerful source of neutrinos for us is our very own star, the Sun. It is a powerful, non-stop neutrino factory. Deep within its core, where temperatures reach 15 million degrees Celsius and pressures are immense, a process of nuclear fusion relentlessly converts hydrogen into helium. This is the engine that powers the Sun and all life on Earth. And as a direct, unavoidable byproduct of this fusion, the Sun releases an unimaginable flood of electron neutrinos. For every 4 protons that fuse into 1 helium nucleus, 2 neutrinos are born. Here, the neutrino's ghostly nature gives it a remarkable advantage. A photon of light created in the core is immediately absorbed and re-emitted by the dense plasma, embarking on a drunken walk that can take hundreds of thousands of years to reach the surface. But a neutrino, born in that same instant, feels none of it. It flies straight out, unimpeded, emerging from the Sun just 2 seconds later and traveling onward at nearly the speed of light. This means the neutrinos streaming from the Sun give us a real-time view of the fusion reactions happening in its heart right now, while the light we see is an echo from the distant past. After an 8-minute journey across space, that solar flood reaches Earth. Right now, as you watch this, about 65 billion of these solar neutrinos are passing through every single square centimeter of your body, every single second. They stream through you, through the chair you're sitting on, and through the entire planet as if you were made of glass. Yet you feel nothing. Not a tingle, not a whisper. Their passage is utterly silent, but the universe produces them in far more violent and spectacular ways. In the final, desperate moments of a massive star's life, its core collapses under its own gravity, forming an incredibly dense neutron star or a black hole. This cataclysmic event, a core collapse supernova, unleashes more energy in a few seconds than our Sun will in its entire 10 billion year lifetime. And about 99% of that energy is carried away not by the flash of light, but by a brief burst of neutrinos. For a few brief moments, a single dying star can outshine the entire visible universe in neutrinos. Closer to home, our own planet is a source. The Earth's crust and mantle contain naturally occurring radioactive elements like uranium and thorium. As these elements slowly decay over geological timescales, a process that contributes significantly to the heat in our planet's interior, they produce a steady, gentle stream of so-called geoneutrinos. By studying them, we can peer directly into Earth's engine room, mapping its composition and heat flow from within. And some neutrinos are the oldest things we can possibly detect. They are ancient relics, cosmic fossils from the very first second after the Big Bang. In that primordial inferno, neutrinos were in constant interaction with other particles. But as the universe expanded and cooled, the density dropped to a point where the neutrinos decoupled, breaking free from the cosmic soup. They have been streaming across the universe ever since, carrying with them a pristine snapshot of the moment of creation. These relic neutrinos form a predicted cosmic background, a faint echo of the Big Bang that, if we could detect it directly, would open the oldest window onto the history of our universe. The story of how we came to hunt for this particle begins not with a discovery, but with a profound crisis. In the early 20th century, physicists were delving into the newly charted territory of the atomic nucleus. They were studying a process called radioactive beta decay, where an unstable atom transforms, spitting out an electron. According to all known physics, this should have been a simple two-body interaction. The parent nucleus decays into a daughter nucleus and an electron, and just like a cannon firing a cannonball, the energy of that electron should have been fixed and predictable. But it wasn't. Experiment after experiment, physicists like Lisa Meitner and Otto Hahn observed something deeply unsettling. The electrons emerged with a continuous spectrum of energies, from almost zero up to a maximum value. In every single decay, a variable amount of energy seemed to simply vanish into thin air. This was a scientific disaster. It appeared to violate one of physics' most sacred and foundational laws, the conservation of energy. This principle, which states that energy can neither be created nor destroyed, was the bedrock upon which all of classical and modern physics had been built. The great Niels Bohr was so troubled that he was prepared to abandon the law of conservation of energy at the subatomic level. For a physicist, this was heresy, a sign of true desperation. The very logic of the universe seemed to be breaking down inside the atom. Then, in 1930, the Austrian physicist Wolfgang Pauli proposed a daring, almost reluctant solution. In a famous letter to his colleagues, which he began, "Dear radioactive ladies and gentlemen," Pauli suggested that the law of conservation of energy was not being violated. Instead, the missing energy was being carried away by a third, unseen particle, a phantom accomplice in the decay. He theorized it must be electrically neutral, otherwise it would have been easily detected. And to account for the energy spectrum, it had to be incredibly light, perhaps even massless. Pauli himself was not confident in this radical idea, famously writing, "I have done a terrible thing. I have postulated a particle that cannot be detected." He called it a desperate remedy to save a desperate situation. For the next quarter of a century, this hypothetical particle, later named the neutrino by Enrico Fermi, remained a ghost in the machine of physics. The monumental task of catching this ghost fell to two American physicists, Clyde Cowan and Frederick Raines. By the 1950s, the world had changed. The atomic age had dawned, and with it came a new, fantastically powerful source of particles, the nuclear reactor. A reactor in operation is a seething cauldron of fission, and a byproduct of this process is a staggering flood of antineutrinos, the neutrino's antimatter twin, trillions upon trillions pouring out every second. Cowan and Raines realized this was their chance. Their plan was audacious. If you want to catch a particle that almost never interacts, you need to throw an unimaginable number of them at your detector. They would build their detector and place it just meters away from the powerful reactor at the Savannah River plant in South Carolina. The detector itself was a clever design, a large tank of water containing cadmium chloride, together with scintillation detectors to capture flashes of light from radiation. This target was sandwiched between layers of a special liquid that would produce a flash of light, a scintillation, when struck by radiation. The entire apparatus was designed to look for a very specific, two-part signal that would be the undeniable fingerprint of an antineutrino. Here's what they were looking for. First, an incoming antineutrino would strike a proton in the cadmium chloride-doped water. This interaction, known as inverse beta decay, would produce two new particles, a positron and a neutron. The positron, being antimatter, would immediately find an electron and annihilate, creating a prompt, telltale flash of gamma-ray light. That was the first part of the signature. The neutron, meanwhile, would drift through the water for a few crucial microseconds before being captured by a cadmium nucleus. This capture would cause the cadmium to release its own secondary flash of gamma rays. They were looking for this unique two-part signature, a flash of light, followed microseconds later by a second, different flash. This would be the smoking gun, a signal so distinct it could not be faked by any other background radiation. And in 1956, after months of careful data collection, they found it. The oscilloscope registered the two distinct pulses, separated by the perfect time delay. After 26 years as a desperate remedy, Pauli's ghost had finally been caught in the act. The confirmation of the neutrino opened a new window on the universe, but it also deepened the mystery. To study neutrinos from more distant sources, like our own Sun, required a completely different approach. Solar neutrinos are far less numerous than those from a nearby reactor, and they are easily lost in the constant rain of other cosmic particles bombarding the Earth. To solve this, scientists went to extraordinary lengths. They built detectors of unimaginable scale and buried them deep underground in mines and mountains, using the Earth itself as a shield to filter out the unwanted background noise. Inside these subterranean cathedrals of science, vast tanks are filled with thousands of tons of ultra-pure water and lined with exquisitely sensitive light detectors called photomultiplier tubes, or PMTs. The principle is beautifully simple. On the rare occasion that a high-energy neutrino from the Sun or a distant supernova interacts with a water molecule, it can knock an electron loose, sending it speeding through the water faster than the speed of light. This creates a subatomic version of a sonic boom, a faint, conical shockwave of blue light known as Cherenkov radiation. The detector doesn't see the neutrino itself. It sees the ghostly blue shadow cast by its fleeting passage. By analyzing the precise timing and pattern of light hitting the thousands of PMTs, scientists can reconstruct a three-dimensional image of the event, determining the neutrino's direction, its energy, and even its flavor, a property we will soon explore. And our ambition has only grown. At the South Pole, the IceCube Neutrino Observatory has turned this concept on its head. Instead of building a tank, scientists have used a cubic kilometer of the pristine, transparent Antarctic ice itself as their detector. Strings of sensors, lowered into holes drilled 2.5 kilometers deep, wait in the eternal darkness. They are not looking for neutrinos from the Sun, but for the rare, ultra-high-energy neutrinos born in the most violent events in the cosmos, exploding stars, supermassive black holes, and colliding galaxies. Messengers from the farthest and most extreme corners of the universe. But as these incredible detectors began to listen to the cosmos, they uncovered a profound and troubling mystery. The first major clue came from deep beneath the Black Hills of South Dakota. Here, in the Homestake gold mine, the chemist Ray Davis Jr. had built one of the most unusual telescopes ever conceived. It wasn't designed to see light, but to catch the ghostly signature of solar neutrinos. His detector was a colossal tank filled with over 600 tons of perchloroethylene, a common dry-cleaning fluid. The idea, as ingenious as it was audacious, was that a solar neutrino, specifically an electron neutrino, would occasionally interact with a chlorine atom in the fluid, transmuting it into a single, radioactive atom of argon-37. By periodically flushing the tank and counting these few argon atoms, Davis could measure the Sun's neutrino flux. The experiment was a monumental feat of engineering, shielded from interfering cosmic rays by nearly a mile of solid rock. For 3 decades, it patiently collected data, and the results were baffling. The theoretical physicist John Barkle had spent years refining models of the Sun's nuclear furnace, calculating with exquisite precision the number of neutrinos that should be arriving at Earth. But Davis's experiment was consistently finding only about 1/3 of that number. This wasn't a minor discrepancy. It was a chasm between one of our best-tested theories of stellar physics and one of our most carefully conducted experiments. The scientific community was split. Was the theory of the sun wrong? Or was there something fundamentally flawed with the experiment? This persistent deficit became known as the solar neutrino problem, and it would vex physicists for a generation. The solution, when it was first proposed, seemed more like science fiction than sober physics. By this time, physicists had discovered that neutrinos weren't a single entity, but came in 3 distinct types, or flavors: the electron neutrino, the muon neutrino, and the tau neutrino, each associated with its own partner particle. The homestake experiment, due to the specific nuclear reaction it used, was blind to 2/3 of the neutrino family. It could only see electron neutrinos. This led the Italian-Soviet physicist Bruno Pontecorvo to ask a revolutionary question. What if the missing electron neutrinos weren't vanishing at all? What if, during their 8-minute journey from the sun's core to the Earth, they were spontaneously changing their identity, morphing from an electron neutrino into a muon or tau neutrino, and back again? This radical idea is known as neutrino oscillation. It suggested that the neutrinos weren't missing, they were merely arriving in disguise. The detectors were simply looking for the wrong thing. It was as if the sun was sending out a stream of pure red light, but by the time it reached us, 2/3 of it had transformed into blue and green, colors our red-only detector couldn't see. It was an elegant solution, but it came with a staggering implication, one that struck at the very heart of modern physics. For this quantum costume change to be possible, a neutrino's flavor state, what we measure in an interaction, must be a mixture of different mass states. And for these mass states to exist and evolve differently over time, the neutrinos themselves must have mass. It couldn't be zero. And according to the standard model of particle physics, our most successful and rigorously tested theory of the fundamental constituents of the universe, they were not supposed to. For decades, the model had been built on the bedrock assumption that neutrinos were massless. If they had mass, even a tiny amount, it meant the standard model, for all its triumphs, was shown to be incomplete. Proving this audacious theory required a new kind of observatory, one that could see all 3 neutrino flavors at once. The challenge was taken up 2 kilometers underground in a nickel mine near Sudbury, Canada. This was the Sudbury Neutrino Observatory, or SNO. At its heart was a giant acrylic sphere containing 1,000 tons of heavy water, a rare and valuable form of water where the hydrogen atoms are replaced by deuterium. This unique target allowed SNO to measure neutrinos in 3 different ways. One reaction was sensitive only to electron neutrinos, just like homestake, but 2 other reactions were equally sensitive to all 3 flavors. It was the ultimate test. If neutrinos didn't oscillate, all 3 measurements would agree. If they did, the electron neutrino count would be low, but the total count would match Bahcall's solar theory perfectly. The results, announced in 2001, were clear and unambiguous. The total number of neutrinos arriving from the sun was correct. They had simply changed flavor along the way. The solar neutrino problem was solved. Neutrino oscillation was real, a discovery recognized by the 2015 Nobel Prize in Physics, awarded to Takaaki Kajita and Arthur B. MacDonald. The discovery of neutrino mass, confirmed by SNO and a host of other experiments, opened a vast new frontier. It was the first definitive experimental proof of physics beyond the standard model. It told us that our best theory of reality was just a chapter, not the whole book. The extreme lightness of the neutrino mass also provides a tantalizing clue. One proposed explanation is the seesaw mechanism, which posits that for every light neutrino we see, there exists an incredibly heavy, unseen partner particle. In this model, the heavier the partner, the lighter the neutrino we observe, like two children on a seesaw. This hints at a possible new sector of particles and physics at immense energy scales, far beyond what we can create in any particle accelerator. And this new physics may hold the key to one of the deepest mysteries of all, our own existence. The Big Bang should have created equal amounts of matter and its mirror image, antimatter. When they meet, they annihilate into pure energy. A perfectly symmetric universe would have become a featureless sea of light. Yet, here we are. Something tipped the scales, leaving behind a tiny surplus of matter, about 1 part in a billion, that formed all the galaxies, stars, and planets. Neutrino physics and leptogenesis are promising explanations for generating this primordial imbalance, but they remain active areas of research. Today, a new generation of colossal experiments is racing to answer the urgent questions this discovery has raised. What is the exact mass of the neutrino? Experiments like Katrin in Germany are meticulously studying radioactive decays to weigh this ghost. Are neutrinos their own antiparticles? And crucially, do neutrinos and antineutrinos oscillate in exactly the same way? If there is even a slight difference, a phenomenon known as CP violation, it could be the smoking gun for their role in creating the matter-filled universe we inhabit. The neutrino, once a theoretical ghost conjured to balance an equation, has become a guide, a messenger from the sun's core, from exploding stars, and perhaps from the very first moments of creation. It has forced us to confront the limits of our knowledge and is now pointing the way toward a deeper, more complete understanding of the universe. We have learned to catch a ghost, and in doing so, we have found not an ending, but a new beginning. A crack in our most cherished theory has opened a window onto a new landscape of physical law. The silent stream that connects you to the cosmos continues, carrying with it the answers to questions we have only just learned how to ask. And with it, the quiet promise that there are still extraordinary wonders to be found, hidden just beyond the edge of our perception, waiting for us to look.